Actually, there's a right and a wrong way to write a compiler. And basically, if you want to design your own language, first of all you need to understand, or you need to decide what it's going to look like. Now, you could use an existing syntax as a base. That's a fairly sensible thing to do, so you could start with a C-like syntax or JavaScript-like syntax. And there's a few different stages that you need to go through. First of all, you have your language definition. And you use what is called a parser generator to produce parser. So there's some very good tools which will help you do that. And there's a particular file format that you can use for various parser generators where you give it a formal definition of what the actual language looks like. What are the different constructs you can use, what are the different types of expressions and so forth. So then you produce a parser, and this is this is in a format which is normally a variation on BNF, which stands for Backus Now For. And Backus and Now were two people who did some very pioneering work in programming language theory, and they defined this syntax for specifying languages formally. So most parser generators use a variation on that. So then you have this parser, which is normally you can generate that. Normally it's a C file, so you generate that and then you compile that into your program. Now, what a parser does is it takes a piece of source code and then it produces the syntax tree. So if we have the source code as input to this, the output of the parser is a syntax tree. So just to give you a very simple example of what a syntax tree would look like. So suppose you've got the expression A is equal to 4 times B plus 5. So this is what the source code would look like in your program. And the parser takes this and it converts it into a tree structure where nodes represent individual things in the expression. So at the top level you would have an assignment statement, and then that would have 2 child nodes. It would have a child node for the variable you're assigning to, and then it would have another child node which is the expression that you're assigning from. So this is a plus expression, and the reason why it's a plus expression is because plus, or the multiply symbol bounds more tightly than the plus symbol. So if you wanted to do 4 times that, then you could put brackets around it. But, and it's up to you when you design your language to specify the bindings and whether these get grouped, multipliers get grouped together or pluses get grouped together. So anyway, we have the plus node, and then on the left side we have a multiply operation, and the inputs to that are 4 and B. And on the right hand side we have the node 5. Okay? So this is the syntax tree representation. And this is a lot easier to work with when you're writing a compiler or an interpreter because you don't have to deal with you separate out all the string manipulation logic. So this does the string manipulation and examines it, and it turns it into the syntax tree. Now, sometimes this is done in multiple stages. So sometimes this will give you a list of tokens. So it will say I found a number, I found a symbol, I found a string, and so forth. And then you can build your syntax tree up from that. Other tools will actually construct the syntax tree automatically for you. If you're working in C, there's two tools that you need to know about, Bison and Flex. Flex is a lexical analyzer that turns this into a stream of tokens. So that is one token, that's another, that's another, that's another, and so forth. Some tokens might be multiple characters. So if you had name equals Peter plus Kelly, then that would be a token, that's a token, that's a token, that's a token, and that's a token. So Flex does lexical analysis. It turns a string into a series of tokens. So this would be ID, and then that's a sign, and then a string, and then add. And then Bison specifies how you take a string of, or Bison lets you specify how you take a string of tokens and then build up the language structure, and then you can build the language tree from that. Just to give an example of what those files look like. So if I'm writing a file for the lexical analyzer, what I basically do is you have a file where you have a series of regular expressions on the left, and on the right you have actions that happen when it finds that particular token. So for example, in this, each of these individual characters are tokens by themselves, and there are some others, like if you have a series of identifiers, or a series of identifier characters, or a series of numbers and so forth, then you create a token of the appropriate type. So this is the lexical analyzer file. And then you have a grammar file, and here you specify all of the reductions in your program. So, for example, here's one where you have a bracket, and then you have a letrec symbol, and then you have a series of letrec expressions, and then you have the in symbol, and then you have another expression. So you define what is the structure, what is the relationships between the different parts of your language. And then you can manually construct the syntax tree here. There's another tool. If you're working in Java, it's another tool called JJ-Tree. And that works with Java C. And JJ-Tree will actually build up the syntax tree for you automatically. So once you've got the syntax tree, then you decide, well, what do you want to do with this? And this depends on whether you're writing a compiler or an interpreter. So a compiler is something which generates code in another language. Usually that's assembly language, but it doesn't have to be. You could have something which compiles your scripting language into C, and then use GCC or Visual C++ to compile it from there. So if you do, there's a fourth year subject called, I'm not sure if it's a third or fourth, is it fourth year? Yeah, if I recommend doing language translators in fourth year if you can, because you'll spend a whole semester learning about this stuff. It's a fascinating subject. So if you're writing a compiler, then what you would do is you would you maybe have some optimizations here. And then you would have the code generator. And then that would output assembly code, which you have your assembler, which compiles it into an executable file. Or if you're writing an interpreter, then you can either work on the syntax tree directly, or you can, so you might have, say, x86 assembly,